Hello everyone, welcome to the demonstration video of ACVTool. ACVTool may help you in reverse engineering, automated testing and malware analysis of Android apps. ACVTool was initially designed at the University of Luxembourg. The name stands for Android Code Coverage Tool. Basically, ACVTool is tracking execution code of bytecode instructions. Initially, we planned using it to improve automated testing tools. It turned out bytecode instrumentation was a really challenging task, resulted in a standalone tool. The research behind ACVTool was published in a top software engineering journal. Recently, ACVTool has received a huge update. Most important, it works now on Multi-Dex applications. Secondly, we don't use APK tool anymore. Instead, we run ACV patcher, which increases the success rate of repackaging. Also, we can highlight now the execution of a selected feature. Finally, ACVTool can shrink applications. To get the full picture of this update, let's check out the internals of the Android application. A simple Android app is an APK file stored on the device. Inside the package you will find assets, libraries, resources, Dex binary executable, and the Android manifest describing app capabilities. Initially, Android was designed to work on simple devices. Only 64,000 methods fit into a single Dex. Android system now supports many Dex files in a single application. We call such applications MultiDex applications. Modern applications include plenty of architecture-dependent libraries and many assets dependent on the device capabilities. That's why Google Play introduced app bundling. As a result, we've got additional applications called split APKs. They may contain platform-dependent libraries, assets, and resources. Here are the ADB commands you can use to explore and download applications from your device. Modern apps are way more complex. They have many APKs, it's way more challenging to analyze them. APK tool helps us to see what's inside the app. We find many directories called Smiley classes. Each one corresponds to a decompiled Dex file. Each folder contains many other short name folders. Inside you can find Smiley classes that reflect the original Java class. This code is heavily obfuscated. It's quite complicated to navigate through such code. ACVTool can help you here, highlighting the actually running code. To start using ACVTool, we take the base APK file. We run ACV instrument command to instrument the app. As an output, we receive the instrumented application package and the serialized code trees of the corresponding Dex files. Now we can install the app and run ACV activate to give required permissions. We are ready to launch and test the app. We run ACV snap to save current coverage information into EC files. We then run cover pickles to apply coverage information on the code trees. From the covered code trees, we can generate the final report. In this example, ACVTool report contains one Dex element which is covered for 7.5%. We can open each class and see executed code highlighted, just like on the example. ACV shrinking is a novel technique to remove not executed code from the app. A very simplified version of shrinking is currently implemented in the ACVTool. We can exclude most of the code from our analysis. Now let's check how to use it on a simple application. For this test, we only want to know what actual code is running behind this roll the dice button. Exploration with the Jadx View, because it's simpler to navigate through the compiled Java code to get the first view. For example, here we see the main package. There is a couple of classes here and here, and there is a list of activities. We can quickly find the main activity, and the main activity has onCreate method and some onChange listener that basically calls show the dice function. And also there is even some vibrator which is vibrating, and of course there is a very interesting functionality called snake listener, or actually shake listener, which is basically trying to catch when you're shaking the phone. Now we will try ACVTool. ACVTool basically is a Python package, so we can just install it directly from pip. It's good to specify the version, and then we can just type acv-dh and it will give us all the commands. Of course, we will start from the instrument. This command will decompile the application, inject its own props into the original Smiley classes, and then it will recompile it into the new Dex file, and the new Dex file will be written into the APK file. And this way we will get the new instrumented application. Let's wait a couple of seconds. So we've got here the pickle file. This is the code tree that corresponds to the Dex file. And now it was built and the new application was patched, and we basically can install it. Yes, it's already here, so we can install it with this link. Okay, I actually like to start my applications with the monkey tool. So here it is, it's already working. We've got our dice function. So what I would like is to measure the functionality of this feature, roll the dice. But when we have started the application, all the instructions have been written in the coverage information data. So basically what we want to do first is to clean it with the flush function. So now we have our coverage as 0. We can start that function. It gave us this dice, and then we can do the snap, which will record our coverage information. Also, after the snap, we do cover pickles. This way we will apply this coverage EC file onto the pickle file. Pickle is the code tree. And we will create a new file, a new pickle that contains already covered code tree. And from this, we can create the report. There is initial information here which is telling us how many lines of this Dex file actually was executed. So it's a preliminary information for the coverage. We can find here 3% coverage. Alright, let's open the report. Here in this report, we can see that there is one element and 3% code coverage. There is also information about lines, methods, and classes, and how many of them missed, which means not executed. If we go inside, we can find many packages. Most of them belongs to Android, also to Google, and we have to find the code written by the developer. This is usually called with the main package name. We can see here the privacy-friendly dicer package, UI, sensors, dicer, and data bidding. And the amount of this code is actually really small compared to all the other packages. So we can try to find anything interesting here. So if we go inside this package, we see different activities. We can go to the main activity and find the executed code here. There is clear dice views, display sum, flash results methods, show dice, which is not fully executed. Basically, if we see green, this means this instructions executed for sure, and there are red color which says that this part of the method was not executed. So this is it. We found some functions that has been executed. And now, if we are interested to reverse engineer how it works, we will be looking into executed functions. What we have seen from this report is that there is still a lot of code that was not executed. We still see a lot of red, which means that we have a lot of code that stays here. There's many methods that were not executed, and it just takes our time to find the green methods, for example here. So what we can do about it, we will try to shrink this code. We will try to shrink it from the report side. We will just add the shrink option in this command and see how it goes. And we open it again. Alright, so this time we've got 64% code coverage. This is because from this report we removed classes. Basically here it says 0 classes was missed. We have now 105 classes, and the same information about methods and the lines. So there is a way less coverage, way less code here to analyze. And when we open the packages, we will always see that in every package we have some or most of the code is green. And we can find the main package. It's here, only 3 folders. Here we have the folder with the main activities. We can always find functions that worked. For example, there is also main activity 6, and here we can find the on-click button, the on-click listener. And what's here? It's also unchanged here, and our vibrator. And the roll the dice function from the Jadx View model. That's pretty much it. That's how we can shrink the application, the report. What else we can do? We actually can visualize it in a better way if we consider the call graph of the methods, which is called method call graph. This is not yet a part of ACVTool, but I have created a small script just to calculate it for the main package, for this one. And it looks like this. In this representation we also see that there is a red dots. So this is a method call graph, and each red dot says that it's an entry point for this package. For example, we can find here main activity 6 on click. Then there are different calls here. There is a main activity 1 on this is a main activity get system service, right? Now it's actually unchanged. Yes, and of course it's moving. And also there is another entry point which is on sensor changed, which is from the shake listener. So basically we have 3 entry points that are working independently in this package. This is pretty much it. Please feel free to try ACVTool. Thank you for your attention.